Scalar multiplication and dot products. So scalar multiplication for a vector, this would be my vector, is usually written with a dot, just like a dot product. Although you could have something like 2v with no dot, okay? But it has something that's not a vector and something that is a vector. And essentially what we're going to get is twice this vector. So this is just going to be 6 minus 8, okay? How about this one? Well, shockingly, negatives come through also. And if you were thinking about this as being a vector that goes over 2 and up 7, okay, if that was the original vector, this would be a vector that goes the opposite direction and half as long, right? So this is -1, negative root 7 over 2. Right? And you could do that entirely with pictures. So if V is, pick your favorite vector, whoop, what's -2V look like? Oh, maybe I made it a little too long. Take that length. 1, 2, that's -2, right? You ought to be able to do that. There's this funny operation though, addition, subtraction, scalar multiplication might be things you're really familiar with, but there's this thing called a dot product. It says if I have two vectors, okay, this is a direction of magnitude, this is a direction of magnitude, I ought to get out a scalar, or I want to emphasize this is a single number. This is not something you can put on the coordinate plane. This is a single number. And what you're going to do is you're going to multiply the first coordinates and add to the product of the second coordinates. You just get out a number. You don't get out a vector. So 2, 1 dot producted with 3, -2 is 2 times 3 is 6 plus 1 times -2 is -2 is 4. That has something to do with, if you drew these two pictures, I'm not going to go into this in too much detail. It has something to do with the area of this parallelogram, okay? And you can certainly Google it to see more about that. Now, what I do want to belabor a little bit is that description, the geometric description. The dot product can also be described as the magnitude of V times the magnitude of W times the cosine of theta, where theta is the angle between them. So you can sort of see if theta was 0, that would be sort of going exactly the same direction, and cosine would be largest it possibly can be, 1. And if they're perpendicular, can you see that cosine of 90 degrees would be 0? So you can sort of see it somehow is related to that area. There's actually, in your textbook, there's actually an explanation of how these are exactly the same meaning. I've defined something sort of two different ways, but those actually have the same meaning, and you can see in your textbook. But let's just spend our time using this definition. Okay, so let's imagine I have two vectors, 1, 3 and 2, 3. I've written them there. And I want to find the angle between them. So how on earth do I go about finding the angle between these two things? And it turns out this geometric description, along with the algebraic way of calculating the dot product, will see me through. I need to do 1, 3 dot 2, 3, the dot product, equal to the magnitude of 1, 3 times the magnitude of 2, 3 times cosine of theta. All of these are numbers. I ought to be able to get to that. But first the dot product. 1 times 2 plus 3 times 3 equals, let's see, this is the square root of 1 squared plus 3 squared, that's 10. This is the square root of 2 squared plus 3 squared, that's 13, times cosine theta. So we got 11 over the square root of 10 times the square root of 13. You can write that as the square root of 130 if you want to, equals cosine theta. Cosine inverse is handy because it knows about angles between 0 and 180. That means that it'll just assume it's calculating the smaller one. You could calculate the other one, but it'll assume it's calculating the smaller one. And in this case, I calculated that ahead of time, and it's about 15.26 degrees. That's the angle there. Hope that's helpful.